Good afternoon. Our project is the Europa Scout trajectory design and analysis completed by Ian Crow, Mateo Berry, Santiago Romero, and myself, Ruben Mora. The purpose of this project is to design a feasible interplanetary trajectory that delivers a spacecraft to Europa while maintaining all mission constraints. Outline. I'll briefly cover the mission overview, explain why Europa is scientifically important, and then describe our mission objective and constraints. The mission overview. The mission objective is to deliver a 3,000 kilogram spacecraft to Europa for long duration observation. The trajectory starts with an Earth launch in February 2031, followed by a Mars gravity assist in May 2031 to gain heliocentric energy. And finally, arrival at Jupiter in September 2033, where the spacecraft is captured into the Europa compatible orbit. Why Europa? Europa is one of Jupiter's Galilean moons and is scientifically important because it likely contains a subsurface ocean beneath an icy crust. This makes it one of the strongest candidates in the solar system for potentially supporting life. Our mission is designed as a follow-up to Europa Clipper, which performs a flyby reconnaissance, while Europa Scout focuses on a substantial orbit delivery. The mission objective. Our goal is to design a valid trajectory that delivers a 3,000 kilogram spacecraft to Jupiter within a 3-year flight time, includes a Mars gravity assist, and stays within the Falcon Heavy launch energy limits. The spacecraft must arrive with the correct velocity for Jupiter capture and retain enough fuel to reduce its orbit towards Europa. We verified using MATLAB, Lambert's problem, and pork chop plot analysis.
Moving on to the mission timeline overview. We launch on February 27, 2031, beginning the first leg of our transfer. That Earth to Mars segment takes around 86 days, bringing us to a Mars flyby on May 24, 2031. After the flyby, the spacecraft enters the second and much longer interplanetary cruise towards Jupiter, lasting 831 days. This brings us to an arrival date of September 1st, 2033, giving a total mission transfer time of 917 days, or about 2.51 years, which meets our mission requirements of being under 3 years. As seen on the slides, our change in V is equal to 0 kilometers per second, as the first two legs rely entirely on ballistic transfer and gravity assist. Moving on to modeling and assumptions. To search for viable trajectories, we use MATLAB software, Aerospace Toolbox for ephemeris data, and Porkchop and Lambert solver scripts provided on Canvas. The underlying theory is that Lambert's problems are used to find trajectories between two position vectors and time of flight. Restricted two-body problems assume that the effect of the spacecraft on the primary is negligible, which simplifies greatly. And interplanetary trajectories can be modeled using the method of patch conics, which is a sequence of individual two-body problems. Some of the key assumptions used in our modeling include coplanar orbits, impulsive maneuvers, and patched conics. Coplanar orbits assume that all planets' orbits lay on the ecliptic. Impulsive maneuvers assume that delta V generated instantaneously instead of over a finite time span. And as for patch conics, interplanetary trajectory can be appropriately described by a sequence of two-body problems ignoring the perturbations of other celestial bodies. Finally, findings and results. Our mass of our spacecraft was 3,000 kilograms, while our C3 was found to be 67.03. This allows for a time of flight of 2.51 years.
The first step in our analysis was to generate a pork chop plot for the first leg of the interplanetary trajectory. In generating this plot, we were able to discover that the launch window was essentially limited to the first half of 2031. The time of flight 1 and launch date for the chosen trajectory can be seen with the star on the pork chop plot. This point corresponds to a launch date of February 27th, 2031, and a time of flight of 86 days. Using the launch dates and time of flight within the maximum C3 contour of the previous pork chop plot, We're able to iterate through trajectories to try to find the appropriate combination of time of flight 1 and time of flight 2. The figure on the right shows all of the trajectories that we found that were viable solutions. The color of the points corresponds to the max delta V capability after inserting into their capture orbit, which is important because that's what we're trying to optimize for to reduce apogee or apoapsis for our final orbit. The chosen orbit can be seen with a circle around it. On the next slide, this slide shows the overall trajectory of the mission. It's worth noting that the eccentricity and the semi-major axis increase from leg 1 to leg 2. Also, there's a heliocentric velocity. The heliocentric velocity turns only about 1.65 degrees. This next slide shows the characteristics of the flyby trajectory. Some of the important things to note are the aiming radius of 3,800 kilometers, the C3 of 277 kilometers squared per second squared, and the minimum altitude of 285 kilometers, which means the spacecraft will not crash into Mars. Finally, this last slide shows the trajectories of the orbits with Jupiter as the primary. The black orbit is the initial hyperbolic orbit. The red is the capture orbit, and the blue is the final orbit with the minimized apoapsis. In order to achieve the initial capture orbit, a retrograde pumping maneuver provides a delta V of 1.18 kilometers per second, which leaves the Europa Scout with a delta V capability of 0.861 kilometers per second. This delta V capability is used in a retrograde pumping maneuver to reduce the apoapsis from 18 million in the capture orbit to 4 million kilometers in the final orbit.
So to summarize, we created a compliance matrix to show how we met our requirements given in the mission with our mission parameters. So first, we depart on February 27, 2031, meets that 2031 to 2032. We have that time of flight of less than 3 years. We do end up flying by Mars. Our C3 at Earth escape is also less than that 70.85 that is required by our 3,000 mass Falcon Heavy rocket. Our final orbit periapsis is also the same as Europa's perijove, which allows for that flyby every so often on its period. And even after that capture orbit around Jupiter, we still have 0.86 kilometers per second of delta V available for those retrograde burns to tighten said orbit. And then obviously, since we made it to Jupiter, we were able to deliver that 3,000 kilogram spacecraft. We were able to do this all through automation, and we were able to identify a handful of feasible solutions, and from this, select the most optimal given the restraints. So first, we identified the launch dates and the times of flight of that first leg to Mars. Then we iterated through all those various launch dates with various things, with matching the infinity, ensuring that the radius of perigee is larger than Mars, capturing the orbital elements once we get to Jupiter, and then also calculating that fuel remaining as we enter that capture orbit. We then determined which solutions had the most fuel, and from there we were able to select the most optimal and calculate all of the elements across the entire transfer. And as a result, as you saw in the compliance matrix, we were able to identify the orbit that exceeds all of the requirements. In the appendix here, we just show the various codes we used and how we used them to achieve this goal. Thank you.